This is kind of a kickoff video to show you a project that we've been working on. First off, introduction. My name is Eric. I worked as a senior staff controls engineer at Tesla. I recently retired, and so I'm kind of joining this project.
I'm Scott Holmes. My background is in oil and gas in Edmonton, Alberta. I'm from Canada, and I've met Eric and the rest of the team through mutual friends and through the Reno Oil races. Back in like 2018 or something like that, 2019, we had the idea of converting my Formula One racing airplane to electric, which we thought was a really cool project at the time, and we thought the speed record was available as well. So we set out to do that. We purchased a motor and an inverter. We designed the system, but then we needed a battery pack. And we went out looking for packs, see what was available on the market, and we found very few packs that would work at the current and voltage that we needed, and that also fit in the airplane. So what we basically arrived at was a custom pack due to the very tight constraints in the tiny little airplane. Now, that custom pack, though, we learned a lot. It was our first time.
Yeah, it was kind of heavy. It was made out of machined phenolic. We had to glue bus bars on. We had to brush glue onto every cell by hand. I can show you pictures of what that battery pack looked like. And so in the process of going through the build of that battery module, we decided to come up with a new design that kind of leverages the PCB industry. Let me give you a quick overview of the battery modules that we've made so far. Both of these modules use a printed circuit board for the battery clamshell. That's basically the tray that holds all the cells. This is a smaller module. This one is a 13S 2P. This larger module is a 15S 19P. And the advantage with printed circuit boards is we can just design any size and shape we want. Any series parallel wiring is also configurable. And this is considerably cheaper than 3D printing a clamshell, and definitely a lot cheaper than investing in capital equipment to do injection molding, for example. With a printed circuit board, we have traces for bus bars, so we no longer have to glue separate bus bars down. And we can also integrate the wiring for the BMS voltage sense leads and individual fusing for the BMS wires as well. Within the 4 layers of printed circuit boards that make up the clamshell, we have voids around clusters of cells so that we can inject glue into one port, and that glue will distribute around each cell. Probably easiest to see from this mock-up we made to kind of prove out our concept. This fixture is a mock-up of 4 cells inside a clamshell, and I'm injecting toothpaste into the void around each cell to show how the glue would distribute in our clamshell. Sort of like how an internal combustion engine has oil galleys that distribute oil to each bearing. So we've talked about the advantages, and let me just show you how we put these modules together. The bottom clamshell is assembled by riveting the stack of 4 PCBs together. We have white circles silk screened on the PCB to indicate where the standoffs get installed.
Okay, so the stripper, we set the cell in, press the cell in like that, spin it until the wrapper is cut, and you can see it's cutting right there. Pull it out, flip it over, and do the other side, like that. Then we grab and we pull, and wrapper comes off both sides like so, and then we simply load into the module, just like that.
Because each cell manufacturer has a slightly different diameter for their 2170 cell, we use a reamer to enlarge the hole to exactly the right size. So now we're going to put the first layer of the top clamshell on. This needs to be a snug fit because it's sealing the adhesive, preventing it from leaking out the bottom. And we're pushing this down until we hit the standoffs. And now we add the intermediate layer, which is our glue channel. Here you can see the cavity where the glue will flow around each cell. And now we're going to add the top layer PCB, which has the bus bars, and this layer also seals around the top of each cell. Because this top layer and bottom layer of the PCBs create a tight seal, it needs to be hammered down. And once all 4 PCBs are installed, we can install these clecos. These align all the rivet holes for the 4 layers of PCB. We install about 75 rivets to make all 4 layers of the PCB one rigid clamshell that's liquid tight for the dispensing process.
This is Hysol 9460 made by Loctite. It's the same adhesive used on several kit planes as well. It's a non-running filled epoxy, 2-part epoxy adhesive. And it comes with a really cool gun and a mixing nozzle. So the 2 parts are in each cylinder here. And then when you pump with the gun, you can see it mixing through the mixing baffles. One is white, one is black, and by the time it comes out the other end, it's gray. So I'm gonna demonstrate the mixing. Actually, down the side, you can probably see it best. You can see the colors flowing.
The static mixer plugs into this hole. We made it so it was a nice tight fit. We inject glue. The glue flows around the cell and eventually comes out of this weep hole. And that's how we know that the cell was completely potted properly. Once the glue on the top clamshell is cured, we flip the module over and glue the bottom clamshell in the same way. Once the top and bottom clamshell are cured, we send the module out to get wire bonded. We will wire bond from this negative bus bar to the rim, and then from the cell positive to this bus bar to the negative rim on the next cell. So this bus bar here is connecting all 19 cells in parallel. So this is our high power connection, and we'll solder in smaller 10 gauge wires all the way across here. And these holes are plated all the way through this PCB, as well as the PCB intermediate layers. This top PCB is double layered, so there's conductors on both sides. And as we build up the layers, the subsequent layers are also double plated to increase wire ampacity. Once the module's been fully wire bonded, we install this protective cover on standoffs to protect the wire bonds from damage. This is what the wire bonds look like. The wire bonds give us individual cell fusing in case a single cell has a short. All there's left to do is solder the high current leads on, and we have a completed module.
Well, thanks, Eric, for explaining all of our latest innovation and technology that we've been working on lately. This is the latest and greatest using all of our lessons learned from many, many failed attempts. We've operated the last pack up to 800 volts. We've blown up several battery packs. I think all of us have been electrocuted at low voltages. Little shocks here and there. Had lots of failed battery packs, lots of failed parts.
Yeah, and so we've put all those learnings into kind of this new product that we hope to sell one day to EV enthusiasts and aviation enthusiasts. So
if you're interested in what we've got here, feel free to reach out. You can comment below. You can reach out to us via DM. We're on basically any of the social medias. Yeah, we'd love to hear your comments too on what you think, or whether you've got ideas for ways to do this better, or so on. I also want to make sure to give credit where it's due. So we're actually a 3-person team, and the third member is unable to make it. He's on the East Coast, unfortunately. We're coming to you from the West Coast. Thomas Lockwood is a big part of this group. He's worked very hard on the design of these packs along with us, but he was unable to make it here today. So want to make sure Thomas is included in that.
yeah, feel free to send us some comments below, and thanks again for watching.